the event, I not even know, I was not in the mood again. But that started like something because I feel like why should I not know it? Everybody else knows it, right? And that was how I started, you know, digging into probabilistic machine learning and just trying to understand, okay, what's the science behind this? The people that know it, they don't have three heads, right? I mean, some might have two, but they don't have three heads. So I can know it too, right? And it turns out it's actually not hard, right? I mean, except maybe even if in your high school days you were like you hated statistics and you hated don't like all those things. But trust me, when you have to relate it to real life problems, it becomes even more interesting. Okay. So I mean I wanted this to be like a live poll, but I changed my mind. So I'm just going to like ask like randomly. Um so if you have the sentence, it will likely rain today. Which of these four options do you think um satisfies it? Is it a probability? Is it a possibility? Is it something else or you don't know? I mean, it's okay not to know. That's why we're here today. I just want to see your answer in the chat. Is it probability, possibility, something else, or you're not sure? Checking the chat now. I want to know. Um, I mean, drop your responses. Feel free. Okay, Taiwo is saying eight probability. I need no, you can just like drop in the chat so that it don't take too much time. Um, is it possibility? Is it probability? Or you don't know, you're not sure. Okay. So I'm seeing okay, you guys are raising your hand. You can just like type it in the chat really so that it's like fast.
Sorry to cut in, but we can't type in due
Oh,
to
you can access the chat.
the admin has turned off chat for external people who are being discriminated.
Ah,
I'm
oh,
joking.
sorry. Okay. Let me see how I can fix that. Um, sorry. I'm going to do that right now. Um, okay. So sorry. Um, I'm not sure why. Um, okay. I'm not sure why it's not um not showing. Okay. So let me just rush through. So there's a difference between probability and possibility, right? Um, Probability is a measure. Possibility is more like a chance. So possibility is when you're just saying, oh, this might happen, this might not happen. But probability is when you're attaching a measure, attaching a figure, a value to whatever you're saying. So if I say that there's a 0.5% chance that rain falls today, that's a probability. If I say, oh, rain falls today, that's a possibility. Yeah, right. Okay, so now why are we looking at probability and why now? Why is it relevant? Right? People are saying that there's no need to learn coding. People are saying that, you know, all this traditional ML stuff, they're going to get faded out. Everybody's going to be using LLMs writing code, blah blah blah, and so on and so forth. But the truth is that the fundamental of even understanding what machine learning is probability, right? So at the very basic, at the very core, probability is so important in not just understanding and also in interpreting, right? Someone's talking about um, explaining, understanding what it means to predict right? We are predicting probability or all those threshold functions. What do they mean, right? How do you measure how do you measure metrics, all those things? Probability is like at the very, very basic. Even for your large language model to know, okay, this is the word I'm predicting next, right? it uses probability in evaluating, like in everything, seriously. And that's why probabilistic machine learning is like super fundamental and also important, right? And also that many organizations still use probabilistic machine learning in their decision making. Talk about in forecasting, right? Time series is basically probabilistic machine learning, right? Right now, people use transformers, they use all, even transformers are also based on probabilistic machine learning, but there are some times where you have to build like really custom solutions, right? And that means that you need to know what you're doing, okay? And also, it's also very useful in developing explainable and fair AI systems. So, I mean, it's okay. Your math is like 1 out of 10, 2 out of 10, 3 out of 10, 4 out of 10, right? It's okay, but um, you can always learn, right? I mean, your biggest roadblock is yourself. So if you feel like I probably don't know it before, but I can know it, right? That means your problem is like half solved because you already have the mind, you're willing to learn. So the problem is when you don't know and then you feel like it's too hard, you cannot learn. That's when you actually not learn. So and if you feel like okay, maybe when we actually start and then things get a little bit complicated, you feel like okay, it's too scary, just try coding it out, right? Try relating it to the Python that you know, try um matching these things to the code, and then it becomes a little easier, right? And I think what I wanted to write there was SkyPy, NumPy. These are like good places where you can like just test out your mathematics skills. And then, of course, I also introduced tensor probability for where you have like more serious applications. So just like you're using probability, but in things like neural networks. Okay. Yeah, so shall we move straight into the practical? I want you to like go to this link on your screen. Let me see if I can paste. So for those that can't access the chat, I don't know if you can access it right now, but if you can't, I'm so sorry about that. Um, you can just like, I'm going to wait. So try to access, just like open the link. I've pasted it in the chat, but if you can access it, just look at the screen. This is going to take you to like a collab notebook, but I'm going to be working from my local system in VS Code. Ouch, light's gone. Okay. All right. So I think does everybody have the link now? If I want to stop sharing. Okay, awesome. Good. Um, I'm gonna share my VS Code right now. Uh, awesome. Sorry, I was. So you should see something like this. So this is my local VS Code, right? And this is the same notebook you see there. You see it here. So I mean, I just said that you should not be scared about mathematics, and then I'm the one saying, okay, someone's raising his hand. You can unmute.
So can you share it to the general group so that I can access the my slide?
The general group. What general group?
Probably the DSN group.
Okay. Let me see what I
Thank
can
you.
do about that. Give me a second. Okay. That's gonna take some minutes. Just a second. So if while I am sending that to the general group, you can like just quickly scroll through. Um, I do assume that you already have like you know probability, right? I mean, it's not a strange term to you. You understand the concept of, okay, will this happen? Will this not happen? What's the chance of A happening versus what's the chance of B happening, right? Um, uh, yeah. Okay, I just sent the link to DSN group now. So what's the chance of this happening versus what's the chance of this other one happening? Um, like that's fundamental to probability, right? But again, probability theory is like a little bit more where, for example, you flip a coin, right? What's the probability that a head shows up? That's 0.5, or a tail shows up, right? Knowing that the sample space, like the sum of all the probabilities in this sample space sums up to 1. So if I give the instance of picking a black diamond card from a pack of 52 cards, right? What's the probability of picking maybe a red card, or what's the probability of picking a black card? Then what's the probability of picking a diamond? All these other things. So playing around it gives you the whole probability theory. So I attached this link here to Deep Learning in Daba's one of Deep Learning in Daba's practical session that I I was a tutor for. So it's like super, super, super insightful. Um, if you Let me try to quickly open it up so that everyone else can see. I'm not really going to what's the word? I'm not really going to uh explain the notebook right here because it's a lot, but I shared it for those who registered earlier, so you probably see it in your email. Here they explain what a random variable is, and you can also like choose your path if you're beginner, intermediate, or expert. So now the gist here is that this was written in JAX. So JAX is like similar to Python. Yeah, JAX is similar to Python, except for like a few notations which you would see. Something like saying a JNP array just is similar to saying, oh, you want to create a NumPy array, right? Just that you're creating a JAX NumPy array, right? And it uses what's called NumPy. So I mean it looks like Python. The print is the same, like everything else is similar, just that JAX is faster than Python. So but again, it's nothing to be scared of, right? So it's okay. So you can just like go through this notebook to like brush up your understanding of probability, what are distributions, what's the beta distribution, multivariate distribution, normal distribution. Um, Beta distribution is just like distribution of two, right? Um, yeah. And the equations, so if you did any statistic course, you probably would have seen this before. I mean, it was too long. I never crammed it, but now here it is. I don't need to cram it anyway. I just need to know how it works. So, like, yeah, it's a really good it is beginner friendly, so don't be scared that, oh, you're seeing a lot of symbols, right? And there's code, so you can test out like things that you're seeing. So it's just like refresh your knowledge on that. I hope you also know what a normal distribution is, right? Where you have that huge bump. Let me see if, okay, I'm not sure there's a diagram to show that right here, but I think in my code I have something that looks like a normal distribution. Okay, great. So let's jump back into our code. Awesome. So yeah, so I also expect that you kind of remember statistics and probability from high school, right? And I did promise to do a brief introduction, which I think I just did, right? And dive straight into Bayes' theorem. Um, so Bayes' theorem arose as a reason for. So for example, right, we have a perfect system where suppose we have a perfect system where I flip a coin, right? It has a head. I flip it again, it has a tail, right? So I'm saying that all things being equal, the coin is a fair coin, right? It's landing on a fair ground, the ground that does not support head. You know what I'm trying to talk about, right? Okay. So um, suppose it's the perfect system, and the probability that the head will always turn up is 0.5, and the probability that the tail would always turn up is also 0.5, right? But given that I have 10 trials, what's the probability that I have, what's the probability of head occurring 5 times or things like that? Okay. Um, Now, so suppose we have more complex scenarios like um, um, rain. Okay, what's the probability that um, okay, maybe what's the probability that rain is going to fall today, given that the sun is at 40 degrees Celsius? So the sun is 40 degrees Celsius right now, but are you sure it's going to rain today? Is it going to rain? Is it not going to rain? You know, in this kind of scenarios, right, we have an existing event, and the event is that the sun is shining right now, right? But then we also want to know if the rain is going to fall, given that the sun is shining right now. So if it was that you can also look at, okay, everywhere is cloudy, the weather is cool, what's also the probability that rain might fall, right? Given that the weather is cool. So when we begin to have conditions where an event exists before, another event happens, right? That's what we call conditional probability, right? That's where we want to, that's where things get more interesting. And so it just forms the basis of an event happening before another, right? So I gave the example that probability that it will rain today, given that the sun is bright. If we represent the probability that it will rain as R, and probability that the sun is shining right now as S, then the probability that it will rain, given that it's sunny, that's probability of R comma S, can be given as, okay, probability that um it will rain, given that um probability that it's sunny, right? Given that it might rain or it has rained before, and probability that it will rain, all divided by the probability that the sun is shining. So, and if we break this down a little bit, right? Um, the probability that sun is shining comprises of all other things. So other things might be happening in the system. So for example, um, there might be probability that it's cloudy, but the sun is shining, it's rainy, but the sun, you know, is also shining, or any other thing that's happening. Maybe there's thunderstorm in a nearby village, or you know, factoring in, so the probability of the sun shining right now sort of is some of all other probabilities, right? But now our main goal is that if it's that, oh, just find the probability that it's raining alone, that's different. But now we're considering the fact that it is sunny right now. And what we call this is that we say that the probability that it might rain, like normally, what's probability that it might rain? Maybe probability that it might rain is 0.2%. Now, what is the probability that the sun, right? The sun will shine, given that, oh, it has rained before. Maybe that's also like 0.7%. So now, I also want to get the probability of the sun shining in all these other circumstances. That would be probability of the sun shining after it has rained, probability of maybe sun shining after a thunderstorm, probability of the sun shining after whatever, right? And the idea is that if I multiply probability of sun shining, give me that rain is falling, times probability of rain, it's supposed to like cancel out. Um, Let me give you the idea of your primary school, okay, let me say secondary school maths, where if I have 2 over 3 times 3, right? 3 is supposed to cancel 3, and then I have 2. So that's like a simpler a simpler notation of getting that sum, but that's not simpler way of visualizing it, where probability of S is the sum of all other probabilities, right? You're taking the sum of everything together. So um, now the probability of A given B is what's called the posterior probability. So posterior probability, I'll discuss this also further, is you're taking the probability given that these events have already occurred. So your it's like I'm measuring a probability after knowing information, right? So and a prior probability is the probability without knowing the state. So I'm just saying, oh, what's probability that it's rain? I don't really know if the rain has fallen before. I don't know if sun has shined before, but I'm just saying, oh, what's probability that it's rain? That's probability without any previous knowledge. That's what's called a prior, right? And then the probability of S, right, is called imaginary probability because it's the sum of all all probabilities where you have that S is called imaginary probability, and probability that S given R is happening is it's called a likelihood. That is, what's probability that this happens given that. Okay. Okay, so I know that that feels like very complex right now, but let's look at this example. Um, in a case where suppose we are testing for a rare disease where the disease affects 1 in 1,000 people, and we're saying that okay, if the disease affects 1 in 1,000 people, so what's the probability that one person gets that disease? That will be 1/1,000. That is 0.001. Okay, and that's the period. That is, this is just the normal probability. Okay, I don't really know how it ascertains to certain regions, but I know that if there are 1,000 people and one person, at least one person in 1,000 people gets affected, then I know that probability that somebody gets affected here is 0.01. Okay, so now a diagnostic test correctly identifies a sick person 99% of the time. So if everybody in among that 1,000 people, right, if everybody goes for a test, the probability that this machine is going to say accurately that, oh, this person is sick or this person is not is 99%, that's 0.99. That is, there's a 0.1% chance of the machine actually misclassifying. I mean, that is fair, like really good in the real world. Okay, so now the test incorrectly identifies a healthy person as sick 5% of the time. This is what we call false positive, where the person is actually not sick, but the person goes and take the test and then says it's sick, just like during that COVID-19 period where some people they're healthy, maybe it's just like normal cold, and then they go take the test and they say, oh, you have COVID-19. And it's the fear of the COVID-19 is what kills them, not really the fact that they had COVID-19. Okay. So um that's like a false positive rate. And a 5% of the time means that the probability is 0.05. So now if we are to compute the probability that a person actually has the disease given that the result is positive. Now look at this. The person did the test, is positive, right? Now, what's the probability that the person actually has that disease, given that the person already has a positive result, right? Okay, that's where you have a probability of A given B, where B is the positive result, and A is the probability that you have the person has the disease. Okay, and we can also see that this is written as the probability of B given A. That is, what's the probability that the person has the disease and the person has a positive result. So the person first has the disease and the result is positive, okay, times the probability that the person has the disease, which is what we already calculated here. So this is the prior here, right? P of A is the prior because we don't really have like a background information on whether the person conduct any test or not, but we just know that probability that somebody here gets a disease is 0.001, okay? And then the sum of all probabilities that all probabilities of having a positive result. So, for example, somebody might have a result, positive result, and the person is sick, and somebody may have a negative result and the person is not sick. So the sum of all these probabilities together give me the probability of somebody having a positive result. Right? So this is what I was trying to explain here. So the probability of B here, right, is the sum of all instances where, okay, I am sick, my result is positive, and I am not sick, but still my result is positive. Okay. So, and that's going to give us the probability that, oh, this person has a positive result and the person is sick. And that's 0.0194. So this is simply just Bayes theorem, right? Like so simple, very simple. And if you're to write that in Python, right? So Bayes theorem, we take the prior of A, we take the likelihood of B happening given A, and we take the marginal probability of B, right? Which is this bottom here. And we say that the posterior of A given B is the likelihood of B given A times the period of A divided by the marginal probability of B. So it's just like you're writing this in Python. And so in our case, the period of A is 0.01, which is this right here. Sorry. Yeah, which is the disease affects 1 in 1,000 people, right? And the likelihood of B given A 0.99. This is here. That is the test correctly identifies a sick person 99% of the time. So this is just
Sorry.
like your, yeah, I
Yeah,
can,
sorry to cut you short. Sorry. Are you still sharing your screen?
yes, I am.
I don't think I can see it here, but I'm not sure. Maybe that's the same for everybody.
I think
Ah,
it's from your end.
I
The
can
screen
see
is visible. Yeah.
it now. Probably not.
Okay.
okay. Okay, phew, that's good. Yeah, and that gives you like the base theorem, simply. Okay, so that's how like you just write base. So you see, it's pretty simple. And now we talked about periods, right? We talked about where this is like your initial belief without seeing any data, right? And we have like three types of periods. We have informative periods, uninformative periods, and conjugate periods. So in Bayesian, you would see conjugate periods like more often because you work with distributions. So when you're working with distributions, you're going to see more of conjugate periods. So informative periods is periods based on strong period knowledge, right? That is, there is a very good chance of this happening, right? Maybe due to belief, due to culture, due to frequency, you know, something where this is there's a strong basis for it happening, right? Why I've not seen the data, but I know that just like saying, oh, what's probability that the sun will shine tomorrow? I mean, the sun comes every day. So there's a very strong basis for me saying, oh, this is the chance that the sun is going to shine tomorrow. And then there is the uninformative period where I mean, it doesn't really matter, right? Like it does not necessarily hold like much information where all the outcomes are equally likely. I mean, it's possible this happens, it's possible it does not happen. It does not really tell us much. And then there's conjugate periods where this results from taking samples from a distribution, right? So posteriors from the same distribution. And yeah, so for example, this is just like plotting. So for example, if I create a beta distribution, right? And I'm saying that, okay, give me the probability density function. So I'm calculating the probability density function from beta distribution, and I just want to plot like I just want to extract samples from that distribution. So that's what's called a conjugate pairs. So there are cases where, okay, I know this, but the times where imagine you have like a real data set, you can plot your data sets, right? And it gives you whatever plots or whatever form or whatever distribution. So now from that data set, you can get like priors, right? Prior information that you can use to train a probabilistic model. Okay. And that prior information is based on the data set itself. Okay. So here I just created like a dummy data set X, and I'm saying that um, I have period X. I have X, right? X as my data, and then I'm generating a probability density function beta, and this is what it looks like. Okay. Okay, so now we've talked about Pyros, we've talked about Bayes, and now we want to talk about Bayesian inference. And Bayesian inference is just simply updating your beliefs, right? Updating your prior beliefs using Bayes theorem. So it's like the more data you have, you want to update your prior knowledge. Like that process of updating and updating is just um is Bayesian inference, and it's it uses Bayes theorem. So it's just like your so for example, my prior I pass it through Bayes theorem, I get a posterior. So now my posterior now becomes my new prior, something like that, as I see more data. Okay, so and this is just like a simple equation. I mean, it's similar to what I already like showed before. It's just yeah. Okay, so discussing about a posterior more. A posterior is an updated probability of an event after considering new evidence or data. Like I said, right? You've seen the period, you used like your current evidence and then combines likelihood and the observed data, combines it together to get an updated probability of an event. Okay, so I saw this on Wikipedia where the beta distribution is more like a conjugate prior probability distribution for Bernoulli, binomial, and negative binomial distributions. So Bernoulli, binomial, these are like two, right? So they deal with like two random variables, say. So binomial, right? Um, coin flips where is it a head, is it a tail, right? That's where we use beta. So I just wanted to like add that in case you're wondering what's a beta distribution. Okay, so for binomial problems, if we take periods from a beta distribution, right, then the posteriors too should also follow a beta distribution. Okay, and this is a very simple representation of saying the same thing. Like I said before, the beta distribution formula is quite long, and I do not intend on putting that in this. You can always look that up. So where you have alpha and beta, which are like your two parameters, okay? Um, and then you have k as a number of success and n minus k as number of failure, where n is the total trials. Just like you have your p and q in probability, right? P is success, number of success, or probability of success, q probability of failure, and then you have your n, okay? And this is how to create um, a simple Bayesian inference using posterior for using beta prior for the incidence of having a coil and using a coin rather, a coin flip. So for example, if I see head 7 times and I see tail 3 times, that means the probability of seeing a head is 0.7, probability of seeing a tail is 3. And then my total number of trials will be 10. That's 7 plus 3. Okay. So my alpha posterior be the sum of my alpha prior and ed. So I'm just choosing these as my alpha priors. Okay. Right. These are my parallels. So here they are the same. So the probability here is the same. This is more like an uninformative parallel where they have like equal chances, right? So I'm saying, okay, at the very beginning, there's an equal chance of missing a head or a tail, right? Okay. So now I can from there generate a better parallel from the, yeah, I can generate a better distribution of the parallels and the better distribution of the posterior, right? And this is the parallel, this is the posterior. Okay. And yeah, they must both be better distributions. Okay. So oh cool. We still have some time. I know I sort of brushed through it, but I think that it's good if you also talk about tensor probability. And tensor probability is a library. Um I'm not sure how many people use it because um it's TensorFlow, right? There also I think PyTorch has a version for probabilistic. I can't remember the name of the library right now, but yeah. So, but I also use Tensor for probability, so that's why I recommend it. You can just like install it. There is a sample code case that we can look at if time permits. I think it'll be really interesting to look at. So this is from TensorFlow themselves, right? So to use, you just install TensorFlow Probability. Make sure you have TensorFlow installed, right? So, ouch, I don't have TensorFlow installed uh, on my system. Okay. Um, how do we run this? Yeah, I don't have. I think I installed it um in a separate environment, not here. Anyways, okay. Um, yeah. So um, after installing TensorFlow, you install TensorFlow, um, and then you need to define like, so if perhaps before you start, you need to like call TensorFlow distributions, and then you define a normal distribution. So if you want to define a normal distribution with the mean at 0, right, and the scale as 1, that's standard deviation. So scale is standard deviation, LOC is mean, okay? And then I want to draw 5 samples from this distribution, right? And I want to compute the probability. Oh shit. This is that. Okay, so this is supposed to show like the samples that I drew and the probability. Um, Let me see if this will run without having my highlight out stuff. Yep, I need to I need to have TensorFlow installed. Okay, so this is where you can sort of try to play around with creating distributions. So there are different kind of distributions, right? Beta, normal, Gaussian, and so on and so forth. So, and the idea is that your data can have these many kind of distributions, right? And each distribution has its own property. So for example, someone working with a Gaussian distribution has there certain properties assigned to Gaussian distribution, right? Versus someone working with a normal distribution. I mean, in the real world, your data set is not likely going to be normal, like, right? So there's sometimes that you have to like conform the data set to a particular distribution so that you're able to perform certain operations on it. So we're saying that, okay, so we generated random data set, right? And also our targets, okay? And we define our periods. So our periods for weights and biases, right? And also, yes, if you've ever wondered, your neural networks, weight and biases are actually periods. So they are either gotten from your data, that's like very basic of neural networks. So if you're going to build a simple neural network, maybe a one layer neural network, right? You often wonder how do models get the value for weights and biases? Usually it's not advisable to start from zero because you run into the problem of finding like local optima. It's like it just continues to be zero, right? So sometimes they also pick like random values also, but again, a more improved way is to use informative, either informed or conjugate spirals, where you pick it from a distribution of data. So that's like how they get your weight and biases. Um, and so you can get the period for weight, period for bias, get the likelihood function. So you can calculate your likelihood from your weight, your data X, and your bias, and then get like a distribution for it. And from here, you can also sample your posteriors and compute the posteriors for your target value, and then you plot. So if these polka dots here are the real data, every of this red line, right, tells me the possible values in the distribution, like the possible target values. If you remember from your basics of machine learning, right, where you're trying to find a line that sort of fits the data. So each of these red lines is telling you all the possible values, all the possible lines that can fit this data in this distribution. Okay. So this is especially useful when you're trying to create a stable, you're using probabilistic modeling, and you're trying to like create stability within your model such that your models, you can sort of have a upper bound and a lower bound, where your model is not just spewing, the accuracy is 0.7 now, and that time 0.2. So you want to be able to like conform it to give a specific range that you know that what's come to worst is between maybe 0.5 and 0.7. So this is useful. This is also this is a good application of that. So yeah, I think that's what I put in the notebook. So this is a very short, simple introduction to basic machine learning. The two notebooks that I shared are super important. I feel like you should read them over and over again. Okay, so we have 8 minutes. I think I would have loved us to go through the what's it called? Um, TensorFlow's notebook, right? It's ouch, my screen is blank. Sorry about that, Amy. Okay. Okay. So I'd have loved us like go through this because it's like really rich. And the part like it's like time series data where you try to predict um looking at CO2 and electricity demand, because this is like a very great use case for probabilistic modeling, and many companies still do predictive stuff, so they need it, they use it. This is where you're using, you're making forecasting with tense probability based on the distribution of the data. um okay, this is the electricity part. So yeah, there are things like Monte Carlo. So I wanted us to discuss Monte Carlo, but I felt like that would be too much for an introduction. But it is also an introduction, right? Maybe the next session we'll talk about Monte Carlo methods, um, variational inference, and that's like where things get really, really exciting. Trust me, really, really exciting. And so I do advise that you go through this notebook, read the documentation to understand like what all this means, right? So you're seeing Keras optimizer. Yes, it's like you're using stuff you use in like artificial, it's like you're using probabilistic modeling bots for artificial neural networks, right? So you're moving a bit above statistical modeling, and you're actually looking at using neural networks, but the concept of probabilistic machine learning. Um, yeah, things get really fun. So I do advise you go through this notebook and also through the two I shared. I'm gonna share them again after this session so that you can um you can like go through them. Okay, so I see that I see that I will ask question. You can ask your question.
I believe. I just wanted
Right.
to. Well, I dropped my question in the chat. Also, okay, maybe we should just take that one first. I dropped it in the chat.
Okay. You said you were gonna ask, but you felt like it was not related to what you're doing. Oh, what Python environment manager? Oh, I used Miniconda. I used Mini. I had like almost 12 minutes. Yeah. So I had like 12 different environments. And so I couldn't even figure which of them had TensorFlow. So so yeah. Any other questions?
Yeah, okay. So the next question is the other resource you were showing, that's the one that has the electricity data set and all. Is it also in the link, the notebook? Is it the resource that you said is from Daba?
And the one I shared with time series, no, that one is in the notebook. I no, that one is in the link that I shared. So that one is in my own notebook. So the one from Indaba, um, it's different. It just talks about, so it starts from the very beginning of what's a random variable and ends at Hamilton. So it talks about Hamilton Monte Carlo method, variational inference, and it goes like in depth, right? But I feel that you might think it's a little bit complicated because the person who did the practical is like a lecturer. So you, of course, the way academics would present things, it's different from the way someone in the industry would present things. So yeah, but there are different notebooks actually. I think what I would do is that I would just share everything again. So I'll share an email with every single thing. Okay.
Yeah,
Um,
that would be great.
and
Thank you.
yeah, great. So any other question? No other questions. Feels like everybody just had a mouthful. Okay. Okay, Boniface. That's like if I got the
Again,
name.
sorry. Yeah, you got it right. Can you hear me?
Yeah, I can hear you.
Yeah, I'm still going to ask about the notebook because I was following, but not too quite well. Where are you going to share it? I don't have access to the chat.
Um,
Yeah.
if you registered for the event, I'm going to share it in your email.
Okay, okay. I think. Thank you very much. I should get it.
Yeah, you're welcome.
How about how can we reach out if we have questions concerning the notebook? Maybe when we try it on our own and we are having errors, or is there any way that we can reach out?
Yeah, you can send me an email. So you can just respond to the email that I use and I'll respond. Yeah,
Right. Thank you very much. That's all from
you're welcome. Someone is asking me if you need to learn beginner ML. Yes, I mean probabilistic ML is not your first entry if you're going into ML because it feels like okay, where do we start? So you need to first understand like what is even a traditional ML, like what's a classical ML, um, and then if you're coming from that background, entering into probabilistic ML makes it make sense to you.
So if you're starting with probabilistic ML first, you probably would not understand why we do certain things or why do we have to do this before this. But if you go and learn like beginner, like normal machine learning first, and then coming to probabilistic ML gives you a lot of understanding. So yeah, I do advise that. Okay. Any other questions before we call it night? Okay, if that's it, thank you so much, everyone, for joining and for making it exciting and interactive also. I would share the resources as promised. So if you've not registered, please register so that I can get them your email. Okay.